4.2, the mean value theorem, part 1. Your objectives for this lesson are to apply the mean value theorem and to determine whether a function is rising or falling based on its derivative. To start, let's look at what the mean value theorem actually is. So the mean value theorem for derivatives says that if y equals f of x is continuous at every point of the closed interval a comma b, and differentiable at every point of its interior a comma b, then there is at least one point c in a comma b at which f prime of c, so the derivative of c, equals f of b minus f of a over b minus a. And this part should look familiar. So this is your slope formula. So basically, this is saying that the instantaneous rate of change will equal the average rate of change at least one point on a closed interval of a continuous differentiable function. And this theorem, like I just said, connects average rate of change of a function over an interval with instantaneous rate of change. Rolle's theorem is related to the mean value theorem. It says that between points A and B on a differentiable curve, there is at least one tangent line parallel to chord AB. That is in your book, more on that in your book on page 186. Example 1. Show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval 0, 2. Then find a solution C to the equation f prime of c equals f of b minus f of a divided by b minus a on this interval. We know that f of x equals x squared is a continuous function because it's a polynomial function. We also know that this curve is a very smooth curve. There's no jaggy, pointy parts, so it will be differentiable. Okay. So we have f of 0, this is one of our endpoints, is 0 squared, which is 0. And f of 2 is 2 squared, which is equal to 4. With this information, the mean value theorem guarantees that there is a point C in the interval (0, 2) for which f prime of c, which is f of b minus f of a over b minus a, okay. So basically we can get to this with the information we've already been over. That is what the mean value theorem tells us, but we want to actually find C. We want to find our C. So let's plug in what we have. A and B are going to be our endpoints, and f of A and f of B are going to be 0 and 4, which we just found. So let's plug those in. So we get f prime of c, and in this case, we know that the derivative of x squared is 2x. So at c, this will be 2c. So 2c equals 4 minus 0 over 2. 2 minus 0. So 2c is 4/2, which is 2. So c must equal 1. That's nice, but what does this mean? What it means is that there is a tangent line, because when we're talking about derivatives, we're talking about tangent lines, to f of x equals x squared at x equals 1 with a slope of 2 parallel to the chord or line segment joining ooh boy, joining point A at 0, 0 and B at 2, 4. Example 2. Let f of x equal the square root of 1 minus x squared. A equals -1, comma f of -1, and b equals 1, comma f of 1. Find a tangent to f in the interval -1, 1 that is parallel to the secant AB. Well, first of all, we know that this function is continuous on the interval -1, comma 1. We also know that this is a differentiable function. If you had doubts about that, the graph is kind of rainbow shaped. It's like this, but more symmetrical. So kind of like that. So as you can see, another smooth curve. So this is also differentiable. Since we are looking to find a tangent to f, let's go ahead and differentiate. So f of x equals 1 minus x squared all to the 1/2. F prime of x will be 1/2 1 minus x squared to the -1/2 times -2x. It's our chain rule again. And -2 times 1/2 is -1, so -x. 1 minus x squared to the -1/2. So -x over 1 minus x squared, square root of that denominator. Okay, so again, this isn't going to exist when the denominator equals 0. So when 1 minus x squared equals 0, or square root, sorry. But if you square both sides, then, you get the same thing. So 1 equals x squared, and x equals plus or minus 1. Okay, so this does not exist when x is plus or minus 1. Okay, so you cannot differentiate or at plus or minus 1. Even though our derivative is not defined at x equals plus and minus 1, that doesn't matter here. So we're trying to apply the mean value theorem, but the derivative doesn't have to be defined on the endpoints for this to work. What we do want to find here, though, again, remember, is that line parallel to secant AB. So let's try to actually find the slope of secant AB. Remember, our y coordinate here is just f of -1. So let's plug in a -1 here. We get 1 minus -1 squared, square root of that, which is 1 minus -1 squared is 1. The square root of 1 minus 1 is square root of 0, which is a 0. Okay, so this is for A. And for point B, let's do the same thing. We have the square root of 1 minus 1 squared, which is square root of 1 minus 1, which is 0. So these really have the same y coordinate at 0. So we have a horizontal line. AB is horizontal, which means that our parallel line will also be horizontal, m equal 0. Okay, and now at what point will this derivative also equal 0? So where will this have a tangent line that is equal to 0? And I'm going to guess right here. Let's see how that goes for us. So negative x over 1 minus x squared, square root of 1 minus x squared equals 0. So if we multiply by the denominator to eliminate that, we're just going to end up with negative x equals 0, because 0 times anything is 0. Divide by -1 to get x by itself, and x is 0. So the tangent line is equal, the derivative is equal to 0. So the slope of the tangent line is equal to 0 when x equals 0. So if we're trying to find the equation of the tangent line that passes through x equals 0 with slope of 0, let's find the y coordinate that goes with that. So let's plug this into the original function. F of 0 is the square root of 1 minus 0 squared. And that's going to go away. The square root of 1 is 1. So we can plug this into our fancy equation here. Y minus 1 equals 0 is the slope, x minus 0, but you're multiplying by 0 here, so that's gone. This is just a 0. And we're left with y equals 1. That is our line. That is the equation of our tangent line parallel to secant AB. Okay, let's look at the physical interpretation of the mean value theorem on page 187. This says, if we think of the difference quotient, f of b minus f of a divided by b minus a as the average change in f over the interval a comma b, and f prime of c as instantaneous change, then the mean value theorem says that the instantaneous change at some interior point must equal the average change over the entire interval. So again, the average rate of change of your interval will at some point equal an instantaneous rate of change on the interval. It's very important. Super important. Yes, I just wrote super important, so you should know that. Example 3. Okay. If a car accelerating from 0 takes 8 seconds to go 352 feet, so 8 seconds, 352 feet, its average velocity for the 8-second interval, you would say, change in distance over change in time. So 352 divided by 8, which is 44 feet per second, or 30 miles per hour. At some point during the acceleration, the speedometer must read exactly 30 miles an hour. So if I'm driving down Ramsey Street and I go, well, I'm at a red light, so I'm at 0 miles per hour, hopefully not driving through the red light. And then at some point, I hit 45 miles an hour, so driving the speed limit. I can't get from 0 to 45 without hitting 30. So let's put this another way. If I drive 30 miles per hour on average, and I'm going between 0 and 45, back and forth, or maybe just up to 45, then I will at some point be driving 30 miles an hour. You cannot skip over it. Okay. Definition of increasing and decreasing functions. We've talked about these before a bit too. Let f be a function defined on an interval I, and let x sub 1 and x sub 2 be any 2 points on I. Number 1, f increases on I if x sub 1 is less than x sub 2, so that f of x sub 1 is less than f of x sub 2. So basically, your smaller x value also has a smaller y value. Bigger x value has a bigger y value. So that would be like right here. That's a really jacked up scale. Let's try this again. Okay. That would be like this. So 1, 1. That's a point. 2 is bigger than 1. 2 is bigger than 1. So when I connect these points, you see that the graph is going up. My smaller x value has a smaller y value, and the bigger x value has a bigger y value. That's why it's climbing. Okay, you have a decreasing function on I if x sub 1 is less than x sub 2, but f of x sub 1 is bigger than f of x sub 2. So this would be our graph. Okay, and maybe I have the point 1, 2, and then 3, 1. So my smaller x value, x sub 1, has a bigger y value. And you see that graph is decreasing. We have a negative slope going down. Increasing and decreasing functions. Let f be continuous on a comma b and differentiable on a comma b. So first one's a closed interval, second one's an open interval. If f prime is greater than 0 at each point of the open interval a comma b, then f increases on the closed interval a comma b. So basically, when your derivative is positive, your function is increasing. And if f prime is less than 0, then your function is decreasing. So when your derivative is negative, so this means negative, you have a falling original function. So your slope is negative. This is positive. It means you have a rising or increasing graph. You have positive slope. Example 4. Determine where the graph rises or falls. Sorry, wait. I don't know why this is then here. I don't know why I wrote that. Okay. So y equals x squared is decreasing on what interval? So let's actually look at our graph here. Well, we could look at the graph. Let's look at the derivative here. So y prime is 2x. We know that. We also know that the graph is going to rise or increase when my derivative is greater than 0. So when is 2x greater than 0? Well, if I divide by 2, when x is greater than 0. Oh, I just did increasing. That's part B. So it's increasing when x is greater than 0. And it's decreasing, if I divide both sides by 2 here, when x is less than 0. And we could write this with interval notation. So decreasing from negative infinity to 0, and increasing from 0 to infinity. Example 5. Where is the function f of x equals x cubed minus 4x increasing, and where is it decreasing? Just like last time, what I want to do here is find my derivative. So it's 3x squared minus 4. And I'm going to, well, increasing. I want to know where the derivative is greater than 0. So that's where 3x squared is greater than 4. X squared is greater than 4/3. Okay. So when we square root this, we end up with two different inequalities. So either x is greater than 2, not 2, the square root of 4/3, or x is less than the negative square root of 4/3. So treat that like division by a negative. Do flip your inequality sign. So this is where it's increasing. And it is decreasing where 3x squared minus 4 is less than 0. So 3x squared is less than 4. X squared is less than 4/3. And when we break this up, we're taking the square root. X is less than the square root of 4/3. And we get x is greater than negative the square root of 4/3. Okay, and this here we can actually rewrite. It's a little sandwich. This one we couldn't have done that, but here we can. So this is where we are decreasing, and this is where we are increasing. Okay. You could have also done this by looking at the graph. You could look at the graph of either the original function or its derivative. So let's do both. Okay. So if we were to look at the original function, it's y equals x cubed minus 4x. So we would have to find our max and our min. And that would take a little bit of work. You could do second trace and do the max there, and then do min. We could have also looked at the graph of the derivative, so 3x squared minus 4x, and when this is positive, so basically from here all the way back, and then from this point all the way forward, that's positive. You know that the graph of the original is increasing, and down here where your y is negative, that's where it is decreasing. So that's how you would look at this graphically. And if you were looking at the graph on your calculator, you would want to do second trace and find the zeros to find those boundary points. And it looks like that is it for 4.2 part 1.